Good morning, everybody. In the last class, I gave an introduction to operational amplifier, and I've given the equivalent circuit of an operational amplifier. And the equivalent circuit is useful for us to analyze the circuit for alternating signals. Now, before going into the applications of operational amplifiers, let me briefly discuss about the block schematic of an operational amplifier. The operational amplifier, as I mentioned, the operational amplifier has a couple of difference amplifiers in the front with differential inputs. It therefore provides differential inputs, and one becomes a non-inverting terminal and the other one becomes an inverting terminal, and the differential outputs are again fed to another differential amplifier followed by an emitter follower, something like a common collector amplifier. Then we go for a level shifter and output driver. So this is a differential amplifier. So this is another differential amplifier providing a gain of, say, differential gain of A1, and this one providing a differential gain of A2, and this one is an emitter follower or a common collector amplifier circuit with gain equal to 1. So this is a level shifter, and this is an output driver, and here is the output mode terminal. We have seen that the differential amplifier has this kind of configuration, and while biasing, we bias the input points at ground potential so that signals can be directly fed in here between the ground and this point. So if the signal is 0, so the input point would be at 0 potential and the signal is absent. So please note that in the common emitter amplifier which you have seen, we were using coupling capacitors to isolate the DC value at the base of the transistor from the input signal. The input signals are usually, if it's an alternating signal, the input signal is usually a zero mean signal. Means it has some part of the cycle for which the signal goes above 0 and part of it goes below 0, and the average is 0. We have zero mean signals, and when you apply such signals to the amplifier, operational amplifier, you should not have any problem. So it is possible only when the base of the amplifier is biased at ground level. Then you can feed a signal around the ground to the base of the difference amplifier. So in doing so, please note that the output voltage here is equal to VCC minus RC into IC, where IC is the biasing current. And this voltage is not biased to be 0, because it becomes difficult for this voltage to be biased around 0. So if this is a 12 or 9 volt supply, so this may be some 4 volts or 5 volts, something like that. But when we take the signal output towards the end of the amplifier, for a 0 DC input, the output voltage should be 0. And that is possible only when the amplifier, the last stage amplifier, is biased around 0 potential. So if you want the this circuit itself to operate around 0 potential. So this voltage, the biasing voltage, should be 0. Please note that if the base is biased at 0 potential, it's not possible to bias the collector at 0 potential because it goes into saturation if you bias this also at 0 potential, and the saturation region is not suitable for amplification. Hence, when the signal is applied around 0 volts, you will get an amplified output around some voltage other than 0. It may be 4 volts or 5 volts or something of that order. But we want, as far as amplifier is concerned, we want the output to be biased at 0. Then how is it possible? It is possible only through a voltage level shifter. You have to subtract some DC voltage. Whatever is the DC voltage you get here, you have to subtract that and see that the output potential is biased around the output stages. Q point is biased around 0 volts. So that's why we need a level shifter, and the level shifter is followed by a driver, and the driver is an amplifier with very low output impedance. Please note that a common collector amplifier gives you very low output impedance. Hence, we have to use a driver which is similar to a common collector amplifier. So the purpose is to make the output impedance very low and at the same time provide you a large signal, output signal. And if after this differential amplification also, we need to make the circuit, since this circuit has some amplification and it should not be loaded by the level shifter and driver, so we need a high input impedance amplifier here. Again, an emitter follower or common collector amplifier can do the job. So this is the block schematic of a typical operational amplifier. I repeat, it has typically two differential amplifier stages, one emitter follower, one level shifter, and a driver amplifier. So this is the block schematic. Different textbooks give you some examples of operational amplifier circuits. So please go through some examples of this type. Otherwise, go through the 741 operational amplifiers users manual. So there you will find the complete circuit in terms of using transistors, resistances, and diodes. Whereas the block schematic is as given below, as given here. And another point which I like to mention is that an operational amplifier, which is called as op amp in short, is a DC amplifier. It can be used to amplify DC signals also. Hence, we cannot use coupling capacitors to isolate the DC from one stage to another stage because it is a DC amplifier. If you use coupling capacitors, this DC is blocked and then you cannot amplify the DC signals. Hence, no coupling capacitors are used in an operational amplifier. Similarly, no bypass capacitor is used in an operational amplifier. Now let us see how an operational amplifier can be used for amplification purposes or applications of operational amplifiers. So it can be used as an inverting amplifier a non-inverting amplifier, that means it can be used as an amplifier with a negative gain, and it can be used as an amplifier without negative gain, and it can also be used as a difference amplifier in certain applications only. Then it can be used as a voltage adder. So it can be used to integrate voltage waveforms, and similarly it can be used to differentiate voltage waveforms. So these are the applications of an operational amplifier. And usually the inverting and non-inverting amplifier application is based on feedback principles. And let us analyze an inverting amplifier circuit. So this is the operational amplifier, this is the inverting terminal, and this is the non-inverting terminal. So this is the output point. So this is the input resistance, and this is a feedback resistance between the output point and the input point. RF is the feedback resistance, and this is the operational amplifier. This is how an operational amplifier can be used to amplify signals with negative gain, and in this particular case the voltage gain can be shown to be equal to the minus RF by R1, which is almost totally independent of the gain of the amplifier. It is only dependent on the feedback resistances R1 and RF. As I explained to you while discussing about the feedback amplifiers, the gain of a feedback amplifier is given by A is equal to AF is equal to A by 1 plus A beta, and when A beta is much larger than 1, this is approximated to 1 by beta. So this is what is exactly done here. Because A is very high and ideally infinity, the gain of the feedback amplifier is dependent on the feedback factor beta alone, and that is equal to R1 RF by R1. Beta is equal to R1 by RF, and 1 by beta is RF by R1. And please note that the feedback is through RF to the input side, and it is to the negative terminal, therefore it is a negative feedback amplifier. If you want positive feedback, so this has to be given to the non-inverting terminal, and there is no reason why we use positive feedback here, because we want stable amplification in many applications. Hence we always give a feedback to the inverting terminal, and what we get is a negative feedback amplifier with negative feedback. So please note that when the input is absent, and if you drive a voltage here, if there is an output voltage here, it is divided between R1 and RF. This voltage is, assuming that this is an open circuit or input impedance is infinity. Please note that V0 is getting divided between R1 and RF, and whatever is getting divided across R1 is the series feedback voltage. Hence it is beta is R1 by RF plus R1 in general, and which is approximately equal to R1 by RF itself. I will show that it is equal to minus RF by R1. Gain is equal to minus RF by R1. Now with this included, the equivalent circuit can be shown like this. Between the inverting terminal and the non-inverting terminal, we have the input resistance Ri here, and this terminal is grounded. This is negative, positive, So this is Vi. Now at the output we have, so Vi as the voltage source and R0 as the output resistance, and so this terminal is connected to the ground, and this is the output potential V0, and between this terminal and the output we have the feedback resistance RF. Now given AV, Ri and R0, we can determine how much of gain we can get. So with this amplifier, with given which is the gain is defined by V0 by V1, and that can be determined by analyzing this circuit. And since both these terminals are grounded, please note that there is a short here. So by analysis using Kirchhoff's voltage laws and current laws, voltage law and current law, we can analyze the circuit and get an accurate expression for the gain of this amplifier. Now the approximate analysis is very simple, and let us carry out the approximate analysis with the input impedance, assuming that the input impedance is equal to infinity and the voltage gain is also infinity or very large voltage gain, and R0 is equal to 0, we get an approximate equivalent circuit. So this is the equivalent circuit. And let the input equivalent input resistance be R1, and this is RF, and this is the input voltage Vi. This is V1. This is the input voltage to the amplifier, and this is equal to AV times Vi. By applying superposition principle here, so this source, the voltage that appears here is equal to R1 by R1 plus RF into AVVI. So that is the voltage that appears here, and due to this voltage alone, so this voltage, output voltage, is equal to, so V1 into RF by R1 plus RF. Now by applying the superposition principle, therefore we can get the total voltage Vi at the input of the amplifier as the superposition of both the inputs, and that is equal to RF by R1 plus RF into V1 plus R1 by R1 plus RF into minus AV Vi. So this can be analyzed in different ways. This can be analyzed in different ways by writing Kirchhoff's voltage laws and current laws, or mesh equations. It can be obtained, or it can be obtained by using the superposition principle also. And what I am using is now superposition principle, that is finding the Vi when this is present and this is shorted, and when this is present and this is shorted. So you get the input voltage like this. From this, Vi can be obtained as a function of V1 in this fashion. It is equal to RF by RF plus 1 plus AV into R1 into V1. And this is approximately equal to RF by AVR1 itself when AV itself is much greater than 1 and AVR1 is much greater than RF. When these two conditions, AVR1 is much greater than RF and AV is much greater than 1, this can be approximated as RF by AV into R1 into V1. Now we get V0 by Vi now. So V0 by Vi is actually minus AV itself. And what we need is the voltage gain with feedback A is equal to V0 by V1. So this can be obtained by from V0 by Vi into Vi by V1 expressions. Therefore, now substituting V0 by Vi is minus AV itself and Vi by V1 is given here. Hence, A is equal to minus AV into RF by AVR1 and that's equal to minus RF by R1 itself. Hence, gain of the amplifier, feedback amplifier is equivalent to minus RF by R1. It's very simple. Please note that this is an approximate expression. And what are the approximations involved here? So the approximations involved are that AV is much greater than 1, AVR1 is much greater than RF, and Ri is equal to infinity and R not equal to 0. So if you want an accurate expression can be analyzed by solving this network for V0 by V1 and you can get an accurate expression for the voltage gain. But by and large, so this expression for this approximation for voltage gain is valid because AV is of the order of a few tens of thousands and AVR1 is also much greater than RF and Ri is of the order of mega ohms. So that means this approximation is valid when R1 and RF are much smaller than Ri and the other approximations which I have mentioned. As an example, if RF is 10 kilo ohms and R1 is 1 kilo ohm, we get a gain of minus 10 in this particular case. And the gain is negative because the feedback is negative here and the input is applied to the negative terminal and therefore there is a phase shift of 180 degrees. Hence it is called an inverting amplifier. Now, I like to explain a very important concept known as the virtual ground concept in the case of an operational amplifier. That means it can be explained in this fashion. When the output voltage is reasonable, that means when the output voltage is of the order of a few volts and it is not saturated and the input voltage is of the order of some millivolts or volts, then the input voltage you find across these two terminals is negligibly small. It is negligibly small. As an example, you consider a gain of 10 to the power of 4 and the output is 10 volts. So what is the input voltage you expect here at the input terminals of the op amp? If the gain is 10 to the power of 4 and output voltage is 10 volts, it's 1 millivolt. The input may be high, input may be a few volts, but at the differential, at the input terminals of the op amp, the voltage is very low, of the order of 1 millivolt. So then only you will have an undistorted output of 10 ohms. If this is say 100 millivolts, the output would be, if the gain is 10 to the power of 4, output would be 1000 volts. And if the amplifier doesn't permit the output to rise to 1000 volts, it gets distorted, it gets clipped, and you get distorted output. But when the input is undistorted and it is of the order of a few volts, it means that somehow the input voltage is of the order of a millivolt. Therefore, when you apply say something like a V1 volts here and apply R1 here, so the voltage drop across R1 is such that only a voltage which is of the order of 1 millivolt appears at the input terminals. If it is more, you won't get a reasonable output here, you will get distorted output here. Hence, always for an undistorted output, so this voltage is almost 0 volts. Hence, it is like a short circuit irrespective of whatever you apply here. Therefore, this is like a short circuit. But is it a short circuit? It's not, because the input impedance at these terminals is equal to Ri, which is Ri, and that is very high, which is of the order of mega ohms. And since this is mega ohms, at the same time the voltage drop can be a few millivolts, so it is known as a virtual ground. Virtual short at the input terminals. And if one of them is grounded, the other terminal is also a virtual ground. The other terminal is a virtual ground. I repeat, this is a virtual ground because for a reasonable output voltage, the reasonable and undistorted output voltage, the input voltage is only of the order of millivolts. But the impedance between these two terminals is very high. Hence, it is not a true ground or true short, it's a virtual short. Although impedance is very high, the voltage is almost 0. That means voltage is almost 0, and what about the current it draws? Current it draws is almost 0. It is of the order of mega ohms, and if this is of the order of millivolts, current is almost 0. Since the current is 0 and the voltage is almost equivalent, 0 volts, it is known as a virtual short between these two terminals. And why is it happening? It is happening this way because of this feedback network. If you apply 10 volts here and say this is R1 is equal to Rf, according to this expression, gain is equal to -1, and you will get minus 10 volts here. For 10 volts here, you will get minus 10 volts here when R1 is equal to Rf, because gain is equal to -1. And when this is minus 10 volts, this is of the order of -1 millivolt. How is it possible, and what is forcing this voltage to be such a low voltage? The high gain of the amplifier is forcing it to be of 0 voltage, and partially the feedback is responsible for it. Without feedback, with 10 volts, it would have been 10 to the power of 5 volts, and the output would have been distorted. And because of the feedback, because the amplifier has a high gain, and because of the feedback, so this voltage is getting fed back onto this side, and effectively the feedback voltage is reducing the input voltage, and it is maintaining a difference of about 1 millivolt that is required for the output to be 10 millivolts, minus 10 millivolts. How is it happening? When this is 10 millivolts, you expect a current to flow through this, and when the gain is minus 1, obviously this will be minus 10 volts. When this is minus 10 volts, and when this doesn't draw any current or negligible current, what happens is current flows through this path. So from 10 volts to, it will flow to minus 10 volts, and the voltage 10 minus 10, the 20 volts gets dropped across R1 and RF. And in doing so, this drop will make it equivalent to almost to the ground potential, so that in spite of high gain, you will get a reasonable output voltage. So the same analysis can be carried out with the help of the virtual ground also. This analysis can be carried out, and we can show that the gain is minus RF by R1 with the virtual ground concept also. So please note that with this is equal to, this is R1 and this is V1 and this is Vi, and Vi now, because it's a virtual short to the ground, it is at 0 volts approximately, and you have the feedback resistance here, RF, and you have the output potential here. Now this is a short circuit, at the same time current is 0, hence the current that flows through this, that is if you designate it as I, the same current flows through RF also, and this is at ground potential with no current. Since it is at ground potential, 0 volts potential, how much is I? I is equal to V1 by R1, and the same current flows through this, and this is at ground potential, therefore V0 is how much? So minus RF into I. This is at ground potential, and RF into I is the further drop. So 0 minus RF into I is this voltage V0. So that is minus RF into I. If you substitute 1 in 2, so you will get this as minus RF by R1 into V1. Hence the voltage gain A is equal to V0 by V1 is equal to minus RF by R1. So using the virtual ground concept, we can analyze the circuit in a much simpler way. And please note that we can take the voltage as 0 when the other side voltage is 0, but the current drawn is also 0. Any questions on the concept of virtual ground and the inverting amplifier? Questions? Why the condition R not equal to 0 is required? It's very simple. To make the circuit simple for us to analyze. So this one also can be analyzed. You will get an expression for the gain in terms of R1, Ri, Rf, R0, AV. So to reduce the analysis or to simplify, we have simplified the model by assuming Ri equal to infinity and R0 equal to 0. For that simple reason, we have chosen that. Any other question? And please note that when Rf is equal to R1, the gain is equal to minus 1. Now let us analyze a non-inverting amplifier circuit. So this is the circuit diagram of a non-inverting amplifier. So naturally we apply the input signal to the non-inverting terminal, and we take the output from the output terminal, and the feedback is negative because we want stable amplification. Hence, the feedback voltage is applied to the negative terminal. Output is fed back through this RF and R1 network to the inverting terminal. Hence, the output is a series feedback, and it is negative feedback, and input is applied here. Now, let us analyze the circuit. With virtual ground concept here, or virtual short concept here, there is no ground here. So, virtual short concept here. If this terminal has a potential of Vi above the ground, so this terminal voltage also will be Vi for a reasonable output. So, assuming that the output is undistorted and reasonable. So, if this is Vi, this voltage is Vi, that means V0 into R1 divided by R1 plus Rf is equal to Vi. And because the input impedance is very high, the current that flows in this part of the network, this voltage gets divided between Rf and R1, and no current flows, practically no current flows through this terminal because input impedance is very high. Hence, this voltage is equal to V0 into R1 by R1 plus Rf, the voltage division between these two. And Vi is the input voltage itself. Hence, V0 to Vi ratio is the voltage gain, and that is equal to R1 plus Rf by R1, and this is equal to 1 plus Rf by R1 itself. Unlike in the case of an inverting amplifier, you have 1 plus Rf by R1 as the expression for the voltage gain. So, in the case of an inverting amplifier. And please note that with the output shorted to the input, so that means when this is infinity and this is a short circuit, Rf by R1 is 0 and the voltage gain AV is equal to 1. When Rf is 0 and R1 is just open circuited, no R1, and if this is a short circuit, we find that AV is equal to 1. It is a voltage follower, and output voltage is equal to input voltage, and the gain is equal to unity. And this is directly shorted to the input. Similarly, we can use the operational amplifier as a voltage adder, or we can use it as a summing amplifier. We can apply different voltages and sum them with different proportions using an operational amplifier. So, this is the circuit for a summing amplifier. And between the ground and each one of these inputs, so if we apply inputs like V1, V2, etc. up to Vm, let us say we have applied M inputs through resistances R1, R2, etc. Rm, and a feedback resistance Rf, and this is applied to the inverting terminal here. And this is a summing amplifier, and the output V0 is equal to minus RF by minus RF by R1 plus RF by R2 etc. etc. is RF by Rm into Vi. It is equal to it is equal to plus V1, V2 etc. Vm. Please note that the output is a sum of all these inputs V1, V2 etc. Vm with different scaling factors. And if we want the scaling factors to be 1, and that means Rf equal to R1 equal to R2 equal to etc. equal to Rm, then this is an absolute sum of V1 to Vm, and with a negative gain, of course, is the output voltage. So the output voltage is sum of all these input voltages with different scaling factors and a negative sign. So this circuit can sum different voltage waveforms. You have a speech signal 1, say speech signal 2, etc., and you can add all these speech signals. Or if you apply different DC signals, it can sum those DC signals. And the gain for individual voltages is given by RF by R1, RF by R2, etc. And this expression can be proved very easily by considering the virtual short principle. By virtual short, since this side is 0 volts, this is also at 0 volts, and this current is V1 by R1, so this current is V2 by R2 and so on, and this is Vm by Rm, and all these currents put together flows through RF, and V0 is the sum current I minus I into RF, and minus I is this V1 by R1, V2 by R2, Vm by Rm, etc. Hence, so this expression can be obtained from this. So this is how a summing amplifier works, and this is the expression for the gain. So any questions on the summing amplifier?